Okay, sorry guys, I didn't see that the time was running out there. So let's just have a 5-minute break and I'll try and wrap up what we were talking about after the break. So sorry for that, for the inconvenience. So let's start again in like 5 minutes. Okay. Okay. So, sorry for that interruption. To finish things off, it's really just like one more sentence. So it was actually good timing for a break, I guess, almost. I was off by 1 minute, I guess. Okay, so let's finish things off. So what we've shown is that phi of gh of x is equal to phi of g phi of h of x. Okay, so let's write that down. And that's true for all x, which tells us that this permutation is equal to the product of these two. And that's what we wanted to know. So phi is a homomorphism. Okay. Okay, so group actions. From a group action, you get information about, like, yeah, you can think about a group actions in terms of group theory, you know, okay. So that is possibly useful to us. Oh yes, so that's the end of the proof. Okay, there's a few properties which we can think about. So the two properties I want to write down are a group action can be free and a group action can be faithful, and a group action can be transitive. Okay. So what do these things mean? I think like transitivity is the most important one, I guess. So an alpha be a group action. Of G on X, meaning that X is a set and G is a group. Okay. So we can say G acts transitively on X if for all X and Y, there exists G with alpha GX equals Y. Okay. So when G acts transitively, it means that for any two elements of X, there's a G that takes you from X to Y. Okay, that's what transitive means. Okay. Not quite the same thing as like transitive relation, but that's okay. Well, it's fine. Okay. I can also talk about group action being faithful. So we could say like G acts faithfully on X if, let's see, I don't want to get this wrong. Okay, if for all G and H, there exists an X such that alpha GX is not equal to alpha HX. Okay, that's what it means to act faithfully. And we'll say that G acts freely on X if for all G and H, if G is not equal to H, then alpha GX is not equal to alpha HX for all X. Okay. Okay, so just to go over it again, group action is transitive if you can get from any X to any other Y. The group acts faithfully if for any two group elements, there's like an element of the set where the group acts differently, the two elements act differently somehow. But a free action is when any two, basically, well, like how I like to think of it is like any two different group elements, there's no relationship between how G acts and how H acts. Okay. You know, so I mean, we just have our three examples so far, so let's see how they stack up against these three properties just quickly. So I'll just draw a table. We had S4 acting on, and there's other examples of group actions, but let's just stick with these. You know, is it transitive? Is it faithful? And is it free? And then we have GL2R acting on R2. And we also have Z acting on Z. Okay. So first of all, S4 acting on 1, 2, 3, 4. Yes, it is transitive. Just briefly, why is that? Well, if I take two elements in 1, 2, 3, 4, there is actually a transposition which takes one to the other. You know, to send X to Y, just take the transposition X, Y. Oh yes, is it faithful? Okay. So if I have two permutations, sigma and tau, the fact that they're different means that they're not equal as functions, which means there's some X where sigma X is not equal to tau X. For some X. Okay, so this is faithful, it is transitive, but it is not free because take G to be the transposition 1, 2, take H to be the identity. Then G of 3 is equal to 3, and that's the same as H of 3. Okay, so it is a faithful and transitive action, but it's not free. It turns out GL2R is transitive, is faithful, and is also not free. And Z acting on Z is all three. It is transitive, it is faithful, it is free. Why is it free? Well, it's just some we can do just like a quick verification of that, I guess. Z acts freely on Z. Let's just try and verify it. So suppose N and M are integers, and N is not equal to M, and let X be an integer. So now we have to check, is alpha NX equal or not to alpha MX? Well, alpha NX is just N plus X. This is M plus X. And if N plus X equals M plus X, then N equals M. No, since N is not equal to M, N plus X is not equal to M plus X. Okay, so the operation of Z acting on itself is, by translation, is a free action. Okay. Okay. So when we're talking about group actions, we have seen how you take a group action and you get a permutation. Okay, so that means what we want to do is take all the things about the symmetric group, which are nice. Well, the main thing that we want to take is we want to take the cycle decomposition and understand it in terms of group actions. Okay. So as an example, let's take G to be this subgroup of S4. It's going to have the identity permutation, the transposition 1, 2, the transposition 3, 4, and the transposition or the product 1, 2, 3, 4. And we'll take X to be 1, 2, 3, 4. Okay. And what we want to do is like we want to try and break apart X according to how G acts. Okay. So notice we can get we can get from 1 to 2. So the transposition 1, 2 sends 1 to 2 and 2 back to 1. and the transposition 3, 4 sends 3 to 4 and 4 back to 3. And the same thing for this permutation as well, right? Okay. So we can actually break apart X into 2 distinct sets. We'll call them orbits. Okay, so here's my picture. Oh, I need to move this up. So when G acts on this set 1, 2, 3, 4, you never leave. It kind of leaves these 2 areas separate. You never jump from one to the other. You can go back and forth. You can go back and forth over here. You can go back and forth over here, but you never join the 2. Okay. So we call these orbits. You just make a little definition. Okay. So that alpha be a group action of G on X let X be an element of X. The orbit of X will be denoted by X in square brackets for now. And it's defined by the orbit. Well, that's just a set of all the things that when you act on X, you get somewhere else, you collect them all and call it the orbit. Okay. And just a quick application of the definition will tell us the relationship to a transitive group action. Okay. G acts transitively on X if and only if X is the orbit of some element of it. And this is true for some X in X. Okay, so a transitive action is just an action which has one orbit. Okay. So to prove this is just you compare the definition of what it means for, you compare what does it mean for X to be equal to the orbit of little x. You compare that to the definition of transitive. You see that that's the same thing. Okay. And we also have the stabilizer. Oh yeah, that's not a proposition, that's a definition, sorry. Okay. Let X be an element of X, then the stabilizer of X, it's denoted by G sub X. And it's just the set of all elements G such that alpha GX equals X. Okay, so we have a stabilizer We have orbits. These are actually related. Okay, so we have the stabilizer, we have orbits. So here we have a subset of G, so let's just prove that it is, you know, hopefully it's a group, a subgroup, so let's prove that. Okay. Stabilizer is a subgroup of G. I guess we should also prove something like, what is the stabilizer of, yeah, what is the stabilizer of, sorry, let me write it. What is the stabilizer of GX? So this should actually be, yeah. Okay. So let's prove these two things. We have to prove something is a subgroup. Okay, that means we need to show that this subset is closed under, we need to show it's non-empty, closed under multiplication and inverses. So first of all, the identity is in GX, since alpha EX is X. That's one part of the definition of being a group action. Okay. Remember, the stabilizer G sub X is, let me just record it here. G sub X is just all the G's such that alpha GX equals X. Okay, now let's suppose G and H are in the stabilizer. And let's look at alpha GHX. Well, the first part of the definition of being a group action is that we have this like associative property like that. And now H is in the stabilizer, so alpha HX is just X. So we have alpha GX, and G is in the stabilizer too, so that's just X. So that's because H is in GX, this is just because G is in GX, we have this. Okay, and that just tells us that GH is in the stabilizer. Okay, and now let's just check that G inverse is in the stabilizer. Also, what is alpha G inverse X? Well, X is really, we can rewrite X as alpha GX. That's because G is in the stabilizer, and then the associative property lets us bring these two together. And G inverse G is just the identity. And one of the properties of a group action tells us that this is really X. Okay, so G inverse is in the stabilizer. And that is enough information to tell us that G, the stabilizer, is a subgroup. And then I wanted to prove this property because we want to see that it's probably not a normal subgroup. Okay. Or if it is, it's kind of weird. Okay, so let's prove. So here, so G sub GX is equal to G GX G inverse. Okay. And through some tricks, it's actually just enough to prove that this is contained in this. Okay. So let H be an element of the stabilizer of GX. So what this means is that, so here GX refers to, again, it's just alpha GX, but I just didn't want to put an alpha in the subscript. Okay. Okay, so what this means is that, so we have GX is really alpha GX, and H is in a stabilizer of that, so we have alpha H, alpha G, and that's equal to alpha GX. And I want to show that H is G times something in the stabilizer of X times G inverse. Okay, in other words, I want to show that G inverse HG is in the stabilizer of X. So let's do alpha G inverse HG times X. And what I want to know is that this has to be equal to X. Okay. Luckily, it will be. Well, and here, this alpha is kind of getting in the way. So I'm, instead of putting alpha, I'm just gonna start a new page and just not put alpha. Okay, so let me just use the notation that instead of, alpha GX, we're gonna write just G times X, because in this proof, there is gonna be so many alphas, it's just gonna be like more confusing than not. Okay, so what we wanna do is look at G inverse H G times X. Okay, and now the associative property of the group action tells us this is really just G inverse H times GX. And then again, if we use the associative property again, that's really just G inverse times H times GX. Okay, now H is in the stabilizer of GX, so H times GX is just GX. Now G inverse times GX is just G inverse G times X. That's by the associative property of these group actions. G inverse G is just the identity. The identity times X is just X. Okay, so this shows that G inverse HG is in the stabilizer of X. In other words, if I multiply on the left by G and on the right by G inverse, we have H is in G times GX G inverse. Okay, so this shows that the stabilizer of GX is a subset of GX G inverse. And now there's like a trick to show the reverse direction. But GX is a subset. Well, GX is really another way to write it. You can write it as G sub G inverse GX, which is contained in G inverse G GX G. And then if you multiply on the left by G and on the right by G inverse, you get G GX G inverse is a subset of G GX. Okay, and that proves that this and this are equal at the end. Okay. Okay, so let us take another break now. Let's start back. So I'll like restart it and everything, and we'll start back at 125 until 150. Okay. Okay, so see you guys in about 8 minutes.